Welcome to the Sisyphus Challenge Week 7. So today we're going to be talking about study diagnostics using the anti-VEGF and kidney failure study that Cindy has been leading as an example. So the original plan was for me and George to do this together. Due to an emergency, George won't be joining us today. So I will begin by walking through the conceptual parts of study diagnostics, and then I will try to log on to our Results Are Shiny app and walk through the user interface with you all. I believe at some point, Patrick will also chime in and help me walk through the user interface as well. So you have probably been seeing this waterfall diagram for weeks now. In the recent weeks, we have been doing things inside the analysis module. So last week we learned about analysis execution. This week is about study diagnostics, evaluating analysis reliability through an objective set of diagnostics. And next week we'll be hearing from Martijn and Jong about evidence synthesis. If you were there at last year's Global Symposium's plenary talk, you may still remember the presentation from Martijn and Patrick on objective diagnostics. And if I were to summarize what they presented, I think the key message is that we need to pay a lot of attention to reduce post hoc investigator bias, including p-hacking and publication bias. And to do that, we need to use a set of pre-specified diagnostics rules to evaluate the reliability of our analyses. And we should not be checking out analysis results until we know that our study has passed the diagnostics. And in last year's symposium, Martijn presented this beautiful diagram about how we can go about this. So again, the central thing is that we need to perform diagnostics before checking out, disseminating, and interpreting study results to ensure that we do not cherry pick the results. And in the very early stage of developing our study design, when we are writing the protocol, we can either write down the diagnostics results in the protocol, or we can write down our diagnostics rules and then follow them when we have the analysis done before looking at the analysis results. And when it comes to study diagnostics, there are actually different aspects. We have to check out the characterization part, and then we need to look at different components of population level estimation. That is how we have done the causal inference part of the study. And when it comes to predictive modeling, we follow the ProBest set of criteria, and I provide a link to the paper that talks about these criteria here. And the criteria are already implemented inside the patient-level prediction package. So in the first part of today's tutorial, I will go through the concepts of certain important diagnostics criteria that we typically do, particularly for the causal inference part of our analyses. And then in the live demo, we'll go through how within the pipeline of strategies, we check the reliability for SCCS and also the predictive modeling part. So the first diagnostics metric that we would like to care about is about statistical power. So statistical power is defined as the probability of detecting an effect if there truly exists an effect. In clinical trials or interventional studies, we typically perform power analysis given our hypothesis effect size and other background information. However, for the Odyssey network studies that we do here, our studies are non-interventional and observational. So the sample size is already there. We already have the data. So we asked the reversed question. Given the available data, what kind of effect size are we able to detect given our analysis design? And the rationale for checking this is that we want to avoid producing hard to interpret underpowered estimates. For example, if an analysis produces a point estimate like this, a relative risk of 6.7, but with a super wide 95% confidence interval, then this piece of evidence is very hard to interpret. On one hand, we have a really large positive effect, seemingly suggested by the point estimate. But at the same time, the confidence interval is really wide, indicating a high level of uncertainty. So in such kind of scenarios, the risk of misinterpretation and misrepresenting the data evidence is really large. So perhaps we only want to keep the kind of evidence that is informative enough so that we don't really misinterpret it. And to do this, we calculate something called the minimum detectable relative risk. So that's the minimum effect size that our analysis is able to detect. So here I'm showing one example in the good case back from the legend hypertension study. So here for a particular target comparator and outcome triplet, I'm screenshotting some cohort diagnostics information and also the study diagnostics MDRR information across multiple data sites. And here we can see that all of the MDRRs are pretty small, meaning that here we do have enough power to detect reasonably small effect sizes. So here, this is kind of a good case. And this is an example of a not so good case. So for a different TCO triplet, again, across multiple data sources, we notice that the MDRRs are rather large. So it means that only for huge effect sizes will our analysis be able to detect them. So that is not very good. That means we do not have enough sample size to say something strong or informative or meaningful. Now, if we do look at the results, our Shiny app, which is linked right here for our anti-VEGF study, then we can notice that the MDRRs across the three comparisons for the IBM CCAE database, I want to mention that I'm only copying certain rows as examples. We do have results right up on there from many different databases now. But across the three MDRs that I'm copying over in my slide here, we notice that we have the ability to detect a 105% of increase in the relative risk. So that's reasonably good enough, meaning that we do have enough power to produce informative, interpretable evidence. So the second thing we want to check on is empirical equipoise. So thinking back to randomized clinical trials, we want to make sure that for all the subjects, they have very similar or basically the same probabilities of getting different treatment options. In a one-to-one randomized head-to-head trial, each subject will have a 50-50 chance to be assigned to the target group or the comparator group. However, for our studies, observational studies, we don't get to assign treatment choices, we only get to observe them. So that means treatment choices can be influenced by patient or provider characteristics because the patient groups are not randomized. And so we would want to use a number to characterize the probability for each patient getting assigned to the target group over the comparator group conditional on their baseline features. And that number is what we call the preference score. So when the preference score is 50%, it means that the chance of getting either treatment for this patient is the same between the target and comparator treatments. Now, what we really care about is that in observational studies, we want to emulate the behavior of randomized clinical trials, which are the golden standards of causal inference. So we want to make sure that we are comparing apples to apples, not comparing apples to oranges. We want to make sure that there is enough similarity between the target and comparator cohorts, and we do it through the preference scores. So we want to see subjects with preference scores between 0.3 and 0.7, which we call empirical equipoise. And we want a large proportion of subjects to fall within this really nice range of equipoise. So again, using an example from the Legend hypertension study, this is kind of a good case example. So for a particular target comparison pair we're looking at here, what we're plotting is the distribution of the preference score for the subjects within the target group in red and within the comparator group in blue. So what is really nice to see is that there's a lot of overlap between the two distributions. So a lot of overlap is a good sign. In particular, in this example, we have more than 90% of people in empirical equipoise. So that's usually really good. And here, this would be an example of a bad case. So for this particular TC pair, we see that there's a lot of polarization between the two distributions of preference scores between target and comparator. So it means that there is not much similarity between the two groups of people. And in here, we have less than 30% of people in empirical equipoise. So that's not very good. Now, going to our anti-VEGF study, our example study for this session, for the target as ranibizumab and comparator as bevacizumab, here I'm presenting again the preference score plots comparing the target group and comparator group. We see that there's indeed a lot of overlap between the blue and the red. In here, we have more than 83% of subjects in empirical equipoise. So that is a good sign. And if we go back to the table that I copied on my previous slide, we see that in terms of the proportion of subjects in equipoise across the three comparisons from the CCAE database, we have really large numbers right here, in particular for the last two analyses. Now, the third thing we care about is covariate balance. Essentially, we want to ensure that the covariates, the baseline characteristics, are balanced out between the target cohort and the comparator cohort after we have implemented certain strategies to reduce the effect of confounders. Now, if you look at the causal diagram here, a confounder means a variable that can influence both the exposure, that is the treatment option, and the outcome. So if there is some effect of confounders, then our effect size estimates can be biased. And so after we have implemented certain strategies to reduce such a confounding effect, we want to check to see if after our adjustments, the two cohorts, the target and the comparator, are now similar enough. So what we check here specifically is the standardized mean difference for each covariate between the target and comparator. Usually, across the literature, we want to see that the maximum of the standard mean differences for all the covariates we care about are less than 0.1. So again, one example of the good case from the legend hypertension study. So in here, for this particular target comparator pair, and using an adjustment method called propensity score matching, we're plotting for each dot the standardized mean difference for each covariate. The x-axis is the difference before we do the matching, and the y-axis shows the difference after we've done the matching. So if we look at the horizontal line of 0.1 right here, we notice that after matching is done, all the SMDs are below 0.1. So that's a pretty good sign, meaning that we have done a pretty good job of balancing out the baseline features between the two cohorts. And now here would be a case that's not so good. In here, we see that after our adjustment, which in this case is propensity score stratification, there is still a fair amount of covariates with standardized mean differences above 0.1. So our adjustment strategy is not doing very well in balancing out the covariates between the two cohorts. And then here, if we check out some results in our anti-VEGF study, the same target and comparator pair in this example, we see that after propensity score matching has been implemented, across all the covariates, we have standardized mean differences that are below 0.1. So in terms of covariance balance, we are pretty good in this particular comparison. Now, another thing that we want to check is about generalizability. So the question we want to ask here is that to what extent can our study results be generalized and applied to the true underlying target population of interest? The rationale here is that although we have implemented a lot of strategies to reduce confounding and to make sure that the two cohorts are similar in order to improve internal validity. But doing so can potentially decrease external validity because we will be tripping subjects away from the analytic cohort, and the composition of the analytic cohort may deviate from the composition of the original target population. And so fundamentally, we want to see a sufficient level of similarity between the target population and the cohort in our analysis. There are two things that we can check on here. So first of all, it is the attrition fraction. We want to see if a substantial fraction of the initial target cohort still remains in the analytic cohort. And secondly, we can also compute the standardized mean differences on all covariates, but between the target population and the analysis cohort. So here, this is, again, one example from the legend hypertension study. If we look at this attrition flow chart here, so that's a flow chart that tells us all of the steps we go through in constructing the analysis cohorts. So we notice that we have put down the counts of the target and comparator cohorts right here. And we compare those numbers with those final numbers of the cohort counts for target and comparator cohorts. Those two numbers don't differ by much. Actually, they're very similar. So in this example, we have almost all subjects in the target population ending up in our analysis cohort. And that's usually a really, really good sign, meaning that we are pretty much doing our analysis on the original target population. And if we also look at the standardized mean difference across all the covariates between the target population and the analysis target cohort, the difference in covariates would be very small. And in this example, if we start with the target population that's really large right here, but we end up with an analysis cohort that's really small. In this case, only a small fraction of target population still remains in the analysis cohort, and that's usually a concerning sign because we would be running our analysis on a very small subset which may not be very representative of the composition of the target population. And when it comes to our anti-VEGF study here, again, we can pull up the attrition flowchart under the estimation tab of the Results Shiny app. And we can compare the cohort counts between the original target cohort and the analytic target cohort. We see that those two numbers do not differ by a lot. And actually, we have more than 74% of target population still remains in the analysis cohort at the end. So again, this is a good sign. Now, the last thing we want to check on is the amount of residual bias. Because of the nature of our data sources, they are observational, and because of the nature of our analysis designs, which may not be perfect in adjusting everything that perfectly matches the settings of randomized clinical trials, there can still exist some amount of residual systematic error even after we have done all we can do. And at Odyssey, we measure the amount of bias using negative control outcomes. A negative control outcome is an outcome that we know has no causal relation to the exposure of interest. And so we would expect a null effect of the exposure on the outcome. But if our estimated effect is not null, then the amount of error in our estimation can help us learn the empirical bias that still exists. So what we do here is we estimate something called the expected absolute systematic error, which is the average of the absolute estimation error in the log relative risk across all the negative control outcomes. Usually we use a set of between 50 to 100 negative control outcomes to estimate this quantity. And then we use the quantity to see if the amount of residual bias is small enough to accept that our calibrated effect estimates can be trusted as unbiased. So at Odyssey, we advocate for empirical calibration, or at least using negative controls to diagnose the amount of bias. But when the bias is too large, then we can't feel very confident or very comfortable to say that our calibrated results are really that trustable because when the bias is so huge, empirical calibration may not be able to fix all the problems. So still, as an example from the LEGEND hypertension study, on the top, what I'm plotting here is the point estimates and confidence intervals across negative control outcomes after calibration. And the same thing, but before calibration on the bottom panel. Graphically, we see that there is very, very little difference between the two plots. And that's true because ease is really small here, meaning that we have very little residual bias. And that also indicates that empirical calibration wouldn't shift our estimation by much. Indeed, if you look at the hazard ratio estimates, confidence intervals, and the p-values, comparing those with those numbers after calibration, they are very similar, and doing empirical calibration wouldn't change our conclusion. And here would be an example where there's a lot of bias and empirical calibration would actually make a lot of difference. In this particular case, notably, before calibration, our p-value is tiny, but after calibration, our p-value is relatively big, meaning that doing empirical calibration, trying to de-bias our estimation would actually change our conclusion. So that is the case that would be a little bit concerning. Now, if we go back to the same target comparator pair in our anti-VEGF study here, what we're seeing is that after calibration and before calibration, our estimates on the negative control outcomes are not really that different. And actually, we have very little residual bias in this particular comparison. Ease is at the level of 0.05, so a really small number. And also at the same time, before calibration and after calibration, our estimation results wouldn't shift by much. So just to wrap up the conceptual part of this presentation a little bit. So I'm kind of summarizing those important diagnostics components that we need to check on, particularly for drawing causal conclusions. And what I'm listing here is actually 3 different sets of thresholds. The first set of thresholds is more like the rules of thumb used widely across the literature. And the second set of thresholds is the set of rules implemented in our strategist user interface. And the third set of rules, if you still remember Martine's talk from last year's symposium, this is what he proposed given empirical analysis of the legend results. So because different diagnostics metrics serve different empirical objectives, sometimes we may want to use different sets of thresholds given our different priorities over the empirical objectives. But what is unchanged across different sets of rules is that we need to pre-specify all of the rules, all of the thresholds, and then perform diagnostics before even looking at the results. Only when our study passes diagnostics can we unblind the diagnostics results. So if you go and look at the results of our Shiny app, you will see that for certain sets of analyses, almost everything is NA, or certain parts are NA. So they are blinded because study diagnostics are not passed by those analyses. So now let's look at the strategist user interface. I'll try to see if we can do a fully live demo on the R Shiny app.
And Fawn, I'm happy to help with this part, but maybe we could just take a quick break to see if there's anybody.
Yes.
First of all, let me just say, Fawn, that was just a spectacular presentation, and I feel somewhat guilty because I definitely think you did a better job of presenting that than Martine and I have done in the past. So well done with that. That was awesome. But Seven, this is new for some people. Why don't we just take a quick couple of minute stop to see if anybody has questions. Cindy, want to make sure this is clear for you and your results, and then we'll absolutely. I'm happy to share the app, and we can go through what it actually means in terms of looking at it in the tools. John? John, you've got your hand raised. Did you want to make a comment?
He's trying to talk, but it's John, if you want to put your question in the chat, that can work too.
Yeah, while we get your audio going. Cindy, I'm curious your impressions. I'll put you on the spot here in terms of, did the diagnostics make sense to you? And did you have any questions about what Fawn walked through?
Yeah, I'm a little surprised. I think it was one of the results was comparing the folks who were getting ranibizumab as compared to aflibercept. That one, those two groups somehow had the biggest difference, which I thought was interesting. So I'd want to dig into that a little bit more because that's a little bit surprising. And I wonder if it's a difference due to like the proportion of our different disease indications in the mixes in these different groups.
Yeah, and so one of the things that we'll go through in the interface is like how you can actually drill into that. What these diagnostic metrics actually provide is a specific kind of scalar score to really oversimplify everything, but at least give us a sense of, does it seem to be good enough or not? But when we drill down into any of those, there's a whole raft of data behind that. So the equipoise statistic is really a single number that's summarizing that entire contour of the propensity score model. And that propensity score model is really just an aggregation of a whole lot of predictors that try to discriminate the groups and understanding the prevalence between those. So all of that we can get into. And as we do the live demo, I'm happy to show that.
Hey, can you guys hear my microphone now?
Yep. Now we hear you,
sorry
Don.
about that. I had to fumble with the mute button. Yeah, just an amazing presentation, an amazing body of work. It kind of blows my mind as I'm a software developer and I'm not nearly as steeped in all of the statistical analyses and all of the data science that goes into this. But it seems, like I said, like just a mind-boggling amount of work. And for what you presented today, what is kind of an estimate of the level of effort? How many people and how long does it take to do this in Odyssey? And then how would that compare to trying to do the same type of work in, just typing away in our studio?
I'll definitely let Patrick answer that because
Okay.
I'm basically a free writer.
Well, you're certainly not that fun, but I'm happy to answer that. So, John, what I'm specifically excited about what we're doing, and part of the reason we wanted to do this whole Sisyphus challenge, is to demonstrate that over the last several years we've been investing a huge amount into all these standardized analytic tools, and Martijn and Mark leading our Hades packages and all of the tools that go into it. We've invested now years of effort to develop these tools. But now we're putting them all together within this strategist framework, which now makes it quite literally possible for you to define a set of inputs, run this package over a few hours, and then have all of these results become part of the standardized output. So, quite literally what Fawn just showed you, if you recall, it was only 2 weeks ago that I showed how to create the input. And it was only last week that I think on this call, I think it was Jenna and Jack showed how to run it. And quite literally the thing that Fawn was showing, those were just the results that came out of last week's presentation. So we are talking about, this end-to-end process being something that if you dedicate your manpower to it, it's something that you can get through in a matter of days, quite literally, to go through that. But the only reason that that's even possible is because of the community effort that went into creating all these standardized tools. If you were to attempt to say, forget the Odyssey tools, I can just go it alone, I couldn't even guess what it would take to try to implement both the large scale analytics that we have, but also all these diagnostics. I think what I've personally taken away from the journey we've been on in this process isn't so much about using other tools, but actually like the act of writing a custom de novo analysis is fraught with opportunities to have bugs. And when we're doing large scale analytics, there's a million places where you could make a mistake, and it's really, really, really super hard to find them. And one of the things that I really appreciate that, Mark has been pushing us on in the community, and I think Martijn does a really great job, is that we are trying to take a software engineering approach to these things that sometimes are considered like academic statistical research kind of stuff, in that, our software has unit tests. We verify that the codes, do the right thing when given a defined input and a defined output. And we're now putting these together into consistent interfaces. And so for me, while I think what we have is pretty groundbreaking in terms of the ability to generate evidence at scale, it's actually the reliability and the quality of the procedures that we're running that is most impactful. Because in absence of that, I go back and think about my own PhD dissertation written with tens of thousands of lines of SAS code, and I can't imagine the number of bugs that existed in that, but thankfully they already gave me the diploma, so they can't, no backsies on that. But I think most people that are doing de novo coding are running a real risk of making mistakes for innocent reasons. And so I'm really passionate about what we are doing here in terms of enabling standardized analytics to get over a lot of the problems that I think bedevil our field right now.
Thanks, really amazing stuff. Thanks.
June, I see you've got your hand raised.
Yeah, thanks, Patrick. You guys can hear me okay?
Yep, we can hear you.
Yeah, thanks. That was a really nice, clear presentation. I have a question. I think from diagnostic perspective, two things seems easy to deal with. When you after matching everything below 10%, that's great. And then after other situations, that a large number of coverages can still after propensity matching still greater than 10%, then you really say the diagnostic tool failed in that situation. But in some situation, you have about dozen of them or just a handful. So either a systematic approach to deal with that, or you go to expert to say those covariates look a little bit deeper, whether associated with outcome or not, or you actually look at those covariates, whether associated with outcome or not. So what the systematic approach, I think that's where proper situation people can look at a little bit deeper around analysis. So I'm just wondering, since the community do a lot of that type of work, can run into that situation easily. We ran into that before. We actually did the manual checking. So I'm just wondering whether the systematic approach or what's a common approach of dealing with those situations.
Han, would you like to answer that, or you want me to take a crack at that?
Yeah, Patrick, can you answer that, please?
Sure.
Okay.
Yeah. Yeah, so I think June, you're mentioning specifically in the context of covariate balance. So when we have a hard rule, like in this case, a pre-specified rule of the standardized mean difference being less than 0.1, by virtue of being a hard rule, it doesn't give you the option of saying it depends, and post hoc saying, yeah, but a few variables were above 0.1, and I'm going to somehow allow myself to wiggle my way out of that. And that is very deliberate and intentional, that we believe you should have a rule that should be followed, and so that you avoid that subjectivity. Now, the value 0.1, there isn't anything intrinsically correct about that value, except, as I think Fawn did a nice job presenting, what matters most is you pre-specify it and you live by the rule that you pre-specified. But it could be possible that one could have different tolerance for that, either being higher or lower. The thing that you raised, June, I think is a, has certainly, we've experienced this where you feel like you're so close to balance, but you're not. And in that there's some variables, and post hoc rationalizing it, you might try to forgive yourself for failing the rule. And indeed, a lot of studies may go through that post hoc rationalization to decide that it would be acceptable. As Martijn outlined in that picture that Fawn nicely showed about the workflow, you could imagine that as long as you don't look at the results, that you could revise your analysis and your thing before you actually look at the results. So you could choose to do that by looking at diagnostics alone. But once you choose that threshold, you really do kind of need, my opinion is you should honor that rule, because that idea that post hoc you say, yeah, but that variable doesn't seem like it could be a confounder is risky from the perspective of, one, you could be wrong about that, and two, you could be just trying to you could be inserting investigator bias through that process.
But yes, I totally agree. When you specify a rule, you try to follow it. But you could look at the blind result, comparative result from that perspective. Can look at those covariates whether associated with outcome or not, right? Is that still biased in that situation?
So a process one that could follow is that before you unblind, you could look at the diagnostics themselves and decide whether or not you're happy with them, and then move forward. And that would not induce any sort of investigator bias. So you'd be iterating through your protocol development and you're establishing your rules. I think a challenge you would face in that particular case is what to do in that iterative process, whether or not you're going to say, let's relax the criteria, or whether you'd say, like, let's fit the propensity score model in some different way, or let's exclude those variables from the propensity score model itself. So there'd be a range of possible ways to do the iteration. The main point would be you'd want to keep yourself honest. You want to stay blinded before you do that.
Okay, thanks.
Amir, I see you've got your hand raised.
Yes. Hey, can you hear me?
Yep, I hear you.
So I just wanted to ask a technical question about the MDRR, because I think in one of the last slides with the table, there was like a mention of infinity to be the decision-making rule for MDRR, right? And based on literature, it's like a number of 10. I was wondering what is the rationale behind that infinity? Because I'm dealing with a question right now that actually wants to pre-specify MDRR. So I'm wondering, should I go for infinity, thinking about, Miguel Hernan works, or I have to specify a 5 or 10 or something? I just want to know what's the thinking of the community in that aspect.
Yeah, I think it's actually a great question here, and I'm going to deliberately table you till next week when Yang and Martijn and Mark will talk about evidence synthesis. But to give you the short sneak preview is with the new approach that Yang and Martijn and Mark have developed for meta-analysis, it enables a site that is extraordinarily underpowered, even to the extreme of only having events in one treatment arm or the other, to actually still contribute meaningful information into a meta-analysis. So that the current thinking is don't throw out a database by itself just because it's underpowered. Instead, allow that to contribute to the likelihood estimate of the meta-analysis. And then at the meta-analysis level across databases, now you can have a question about adequate power.
Got it. Thanks.
Andrew?
Yeah, was the if I understood it correctly, the generalizability criteria was less than 1, and it seemed like it had to be by definition if it's a proportion of the target cohort. And does that mean that that's a work in progress that a graduate student or somebody might take on as like, here's how we do it, or here's a heuristic for tuning it to the question given some other parameter or some other kind of a thing? Is that a work in progress that somebody could contribute to, I guess is the question.
So the just objectively, you're exactly right, Andrew. The threshold of 1 basically means it's not imposing a restriction. So no study is getting kicked out on the basis of that. And I would strongly encourage any students or trainees on the line that are thinking about research areas is thinking about what other diagnostics could be brought to the fold as part of this process, and also, as I think Fawn did a nice job presenting, what could potentially be the thresholds that one could choose to evaluate to understand their implications. So right now we don't have evidence to suggest that generalizability threshold by itself makes sense. Not to say that it doesn't, but we don't have the evidence for that, and so we're evaluating it, but we're not using it as a decision-making criteria.
Thanks.
All right, Fawn, I'll do my best George impersonation here, and we'll go through the live tool. I know we've got only 7 minutes left here, so I'll share my screen. So what Fawn just presented very nicely is the conceptual rules, and you also saw some very pretty tables that she made that showed the results of the anti-VEGF study. All of those results were extracted from the R-Shiny app that has been made publicly available. I will post the link to this in the chat as soon as we're done here, but hopefully it won't crash while we're going through this. The main thing to highlight here is that for all of you who are data partners who can execute the study, so John, looking at you, since you said this is remarkable, I hope you'll run this on your data, as well as everybody else to contribute to Cindy's study. Once you run the study, you can upload, or you can share it, upload the results, and the results will then be made available through this user interface. This user interface is what we saw last week in the study, at the end of our study execution step, whereby on the left-hand side, there are tabs where you can explore the cohort diagnostics results. the characterization results, the prediction results, and the estimation results, which are both cohort method and SECS. Just to quickly show you where Fawn got those results, and also to dive into even the fact that there are much more results. I'm going to start here for a comparative cohort design. When we click on this tab, we get here to be able to look at the Evidence Explorer. And in this view, there's both a tab for the diagnostics as well as a tab for the results. In this tab for the diagnostics, every row in the table represents one of the analyses that was executed. So for example, just to read across this row here, the Optum SES database running the cohort method with an on-treatment time, comparing aflibercept to ranibizumab for end-stage renal disease. You see the associated measures that Fawn went through. So maximize standardized mean difference is that statistic we use for covariate balance, equipoise, minimum detectable relative risk, that attrition fraction that could be used for generalizability, and the expected absolute standard error. So each one of those are like the quantified values that you'd see. And then the columns to the right of that show you whether or not they pass or fail the pre-specified criteria. So we can see here, for example, the balanced diagnostic passed, the equipoise diagnostic passed, the minimum detectable risk passed, and so on and so forth. And so at the end, we actually basically have a flag which says, are we going to unblind the results or not? And this table contains all of the databases, all of the analysis, all of the comparisons, and you'll see that sometimes we fail a diagnostic and therefore we will not unblind. And sometimes we pass all the diagnostics and then we will unblind. But that's something that the software actually governs in this process. So this first tab basically just shows you what the final summary diagnostics are and whether or not we pass. When we go to the tab for the results, we're able to select a comparison of interest. So here I've selected aflibercept versus ranibizumab. And here we can see that there are in fact 6 databases results that have already been loaded up. And if we look at this table, you'll notice that, so I've got 6 databases shown here, but in fact, only 3 are providing results. And that's specifically because the 3 that are sharing results are those that have passed all of our pre-specified diagnostics. And those that say NA across the board, those are the ones that have failed diagnostics. If I'm interested in one of these, I'll start with one that failed diagnostics to illustrate it. I could select the Medicaid database, which fails. And we can scroll down and we can see in the drill down, we can see that there were 700 patients in each group. We can get to that attrition table that Fawn showed. So you can see we started with 2,300 and we ended up with 700. So we lost about 2/3 of our patients. I can click on the propensity score tab to look at that equipoise to see whether or not there's decent overlap between the groups. And in this case, it looks kind of okay. I can click on covariate balance, and this is going to show me whether or not all the variables achieve a standardized mean difference of less than 0.1. And so here we can see one of our failures. So Cindy, as an example here, you're saying that you were a little bit surprised. Why are these groups so different? Well, actually, all of these variables we could actually even highlight over. And just to show you as an example here, these 2 groups before matching were quite different in terms of their proportion of diabetes, as an example. And even after propensity score matching, they still had a standardized mean difference of 0.15. And so this is a case where in the Medicaid database, for this specific comparison, in this database, we were not able to adequately adjust for diabetes. And in this case, we could easily imagine diabetes is highly associated with end-stage renal disease. So that's a clear confounder, and we wouldn't want to move forward with that. The last tab illustrated here would be the systematic error. Here we can see using our negative controls that we didn't observe some sort of systematic error. So in this case, we just went through the diagnostics and the drill down of the database that failed, and we see indeed we have a risk of confounding, and therefore we don't want to unblind that. In contrast, if I were to take that CCAE database that Fawn showed, we could look at the same thing like the covariate balance, and what we will see is that indeed we're able to get those variables to be better adjusted. We see that the systematic error still looks good. We see that the attrition still looks good. So you're able to go through each of these comparisons and drill down to the specific information. Ultimately, the final answers that we're going to be interpreting, and next week, Yang and Martijn will go through the meta-analysis, is if this was our whole study, which of course it's not, we're going to get lots more data partners hopefully to be incentivized to contribute. But in this case, what we would see is we have 3 databases that have passed diagnostics that are producing estimates. So when we go to do a meta-analysis, we will use those 3 databases because they are the ones that we determined individually may be sufficiently reliable. These 3 other databases, we would report that we attempted to run the analysis on them. However, they failed diagnostics for an associated reason that we will be able to fully summarize. And so for each of the pairwise comparisons, we can select the analysis we're interested in and drill down to be able to look at the specific diagnostics. And I know we're at time now, but the exciting part that I just share with you is this framework, which is being applied for our study on anti-VEGF treatments, is the exact same framework we apply to all 4 of our Sisyphus Challenge studies. So if you join at 7 p.m. Eastern time, you'll be able to see that. Now I've just flipped over. Now I'm looking at fluoroquinolones and aortic aneurysms, and it's the exact same app with the exact same analysis, producing the exact same diagnostics. It's just that now we have different results because we're answering a different clinical question. I encourage all of you to play around with the application itself. The user interface is something we're still, of course, doing a lot of active development on, so also welcome feedback about that. But what I want you to take away from Fahn's presentation is that we have these diagnostics that are not just a conceptual idea, but they've been fully implemented within the strategist framework and made accessible directly in the user interface. So all of you who are participating in this study and are following Cindy's lead can go explore these results, think about what they're telling us, and certainly encourage all of your colleagues who have access to data to run the study similarly, and so that you can produce these results and contribute it to Cindy's study. So with that, I'll stop and turn it back to Craig. Thank you all.